This is the 2012 Queensland Senior External Exam Physics paper. We're looking at paper 1, part B, short response, question 10. First of all, we read the question. A two-point source interference experiment used to determine the wavelength of a monochromatic light source has a screen placed exactly 3 meters away. If the slits have a 0.0500 millimeter separation and the dark fringes on the screen have a uniform 3.30 centimeter separation, what is the wavelength of the light source? Having read the question once, we now go back over the question and make sure that we identify all of the important pieces of information. So it's a two-point source interference experiment. It's a monochromatic, which is one wavelength of light, and there's a screen 3 meters away. So we highlight the 3 meters, two significant figures, the unit being meters. If the slits have a 0.0500 millimeter separation, so that's a 0.05 millimeter with 3 significant figures, we'll need to change that into meters to make sure we're in SI units. And the dark fringes on the screen have a uniform 3.3 centimeter separation. So 3.3 centimeter separation, we need to make sure that we change that centimeter into meters, and so therefore we've got one unit through the problem, meters being the unit for distance. Now the question asks us to calculate the wavelength of the light source. Right, now that we've read and identified the information, we now need to draw a pattern. So having a look through it, it's a two-point source, and so we have two gaps here in our screen, and we have a light source behind the screen. The light goes through these gaps and diffracts out, and we get an interference pattern, and with our interference pattern that's projected onto a screen. So we can go through and we can label a few measurements. The slits have a separation of 0.0500 millimeters, so we can write that in as our distance D, the separation of the slits. The screen is a distance of 3 meters away, so we make sure we write that to two significant figures as well. And we have a central maxima on our screen, then we have a minima, then we have our first maxima, then we have our next minima, and on the opposite side it's exactly the same symmetrically. And so our dark bands here are our nodes where destructive interference occurs, and we know that the separation of these dark bands here is 3.3 centimeters to two significant figures. That's our delta X value, or our separation. So there we go, there's our diagram drawn. We now need to decide how we're actually going to go about and solve this particular problem. So it's time to have a look at our formula sheet. Our formula sheet starts off with all these kinematics values here at the top. We're on to the second part of the exam, and so we're into the light section. In the light section, we see a formula here. Delta X equals L lambda on D. There it is right there. Delta X equals L lambda on D. Let's have a look and see whether that's going to be the right formula to do this particular problem. Right, we're after lambda, so I need to make lambda the subject of this equation. So I need to multiply both sides by D. The D's will cancel out, which will give me delta X times D. And I also need to divide both sides by L. L's will cancel out. And so I can work out my wavelength by doing delta X times D on L. Let's have a look at our values. Delta X is 3.3 centimeters, D is 0.05 millimeters, and the length our screen is away is 3 meters. So I should be able to put those values in and do this calculation and calculate my wavelength. So now let's lock in the values. Delta X, 3.30 centimeters. Now I need to have a uniform unit of distance, and that uniform distance will be in meters or SI units for the distance. So to 3.3 centimetres is multiplied by 10 to the negative 2 to put it into metres. D is 0.0500 millimetres, so multiply it by 10 to the negative 3 to get that into metres, and we divide that whole lot by 3 metres. So now I've locked in my values. I can now do my evaluation. So I get my calculator, make sure that we've got that. So I'm multiplying 3.3 by 0.05 and dividing that by 3. And when I do that calculation, I get 0.055. So let's put that in 0.055. Now I need to multiply that by 10 to the negative 2 and 10 to the negative 5. 10 to the negative 2 and 10 to the negative 3 is 10 to the negative 5, like so. Now, to get this in standard form, I've got to make it 5.5 by 10 to the negative 7 metres. Next thing I need to do, once I've done my evaluation, is to now look at whether my answer makes sense. That's around the wavelength for visible light, 550 nanometers. Significant figures. This has 3 significant figures. This has 3 significant figures. This has 3 significant figures. I need to have 3 significant figures in my answer. 5.50 by 10 to the negative 7 meters. You could also express this in the terms of nanometers. Nano, of course, is 10 to the negative 9. So that's just moving the decimal point 2 places to the right and changing 10 to the negative 7 to 10 to the negative 9. Now I need to always make sure that I express my answer in the terms of the question that's asked. So what is the wavelength of the light? So for the examiner, to make it absolutely clear to him that we have answered the question, the wavelength of the light is lambda equals 550 nanometers, which is 5.5 by 10 to the negative 7 meters. Either one of those two answers there would be appropriate. For the particular marking scheme, this particular question is only worth 2 marks. So you get 1 mark for putting the numbers into the formula, and you get 1 mark for doing the correct calculation at the end. There's your 2 marks for this particular